Have you ever been in a window seat just staring out at that giant wing and thought to yourself, how in the world does this actually work? How does this massive machine weighing hundreds of tons just defy gravity and soar through the sky? Well, today we're going to break it all down. We're going to decode the science of flight. And it all starts with what seems like an impossible problem,
right? It really feels like it shouldn't be possible. How can something so incredibly heavy just float? It's like a giant puzzle. But trust me, by the end of this, we are going to have all the pieces right where they belong.
And this is the real question, isn't it? I mean, getting off the ground is one thing, but how do you stay up there, stable, in control, for hours on end? So let's dive into the physics that makes this incredible feat an everyday reality.
Okay, so to get flight, you have to understand that every plane in the sky is in a constant tug of war with four invisible forces. You've got weight, gravity, always pulling the plane down. Fighting that is lift, the upward force that keeps it in the air. Then you have thrust from the engines, pushing it forward, and battling against that is drag, which is basically air friction holding it back. Every single second of a flight is a delicate dance between these four fundamental forces.
Now, you might be thinking it's all about those huge engines, right? Just raw power. And yeah, thrust is absolutely essential. But the real secret to flying, the real magic, isn't the machine. It's the invisible stuff it's moving through, the air itself. So, the first thing we have to do is get rid of the idea that the sky is just empty space. It's not. Air is a physical substance. In fact, scientists call it a fluid, just like water. It's a literal sea of gas that has real weight and real substance. And if you can control a fluid, well, you can use it to do some pretty amazing things.
So what does this number mean? Get this. At sea level, the air is pressing down on every single square inch of your body with 14.7 pounds of force. That's like balancing a bowling ball on your thumbnail. That's the kind of substance we're talking about here. That's what we have to work with.
And this right here, this graph shows us exactly why airplanes fly so incredibly high. As you go up in altitude, there's just less air above you pushing down. That means the pressure drops, and so does the density. The air literally gets thinner.
So, why fly in thinner air? Well, it's all about efficiency. The thinner the air, the fewer particles there are for the plane to push out of the way. And that means less friction, less resistance, which is what we call drag. The plane can fly way faster and burn a whole lot less fuel.
Okay, so we've established air is a physical thing we can actually use. But how? How do we use it to create that incredible upward force, lift? Well, the answer lies in the absolutely ingenious design of the airplane's wing. It's also called an airfoil, and honestly, it's the hero of our whole story. Just look at this shape for a second. See how it's not symmetrical? It's got that beautiful curve on the top, but it's much flatter on the bottom. Now, that is not an accident. It's a precision-engineered tool designed to slice through the air and basically trick it into lifting thousands of pounds off the ground.
So, how does this shape work its magic? It all comes down to a fundamental law of physics called Bernoulli's principle. And yeah, I know, the name sounds a little intimidating, but the concept itself is actually beautiful and simple. Let's just boil it down to this. This is the key. When a fluid, like air, moves faster, its pressure goes down, and where the air moves slower, the pressure stays higher. That's it. That's the trade-off. Faster air, lower pressure. Slower air, higher pressure. Just lock that in. And here it is. This is the aha moment. As that wing cuts through the air, the curved top makes the air molecules traveling over it go a longer distance, so they have to speed up to meet the air from the bottom at the same time. The air underneath has a shorter, straighter path, so it moves slower. And what did we just learn? Faster air on top means lower pressure, and slower air on the bottom means higher pressure. So you get this amazing pressure difference. The high pressure below pushes up, and the low pressure above actually pulls up. That difference, that is lift. In fact, something like 75% of a wing's lift comes from that low-pressure vacuum effect on top. Incredible.
All right, so the wing gives us lift, and that beats weight. Awesome. But flying's a lot more than just going up, right? To actually fly straight and level, the airplane has to constantly manage all four of those forces we talked about at the beginning.
When a plane is just cruising along smoothly, we say it's in a state of equilibrium. Think of it like a perfect stalemate. The upward force of lift is perfectly balancing the downward pull of weight. That keeps the altitude steady. And at the same time, the forward push of thrust is perfectly canceling out the backward pull of drag, and that keeps the speed constant. Now, let's talk a little more about drag. You can just think of it as air resistance. It's the price you pay for moving through the air. And this graph shows something really cool. There are different kinds of drag. As you go faster, the friction from the plane's shape becomes a bigger deal. But when you're going slower, the very act of generating lift creates its own kind of drag. The goal for any pilot is to find that perfect sweet spot right in the middle, the point of minimum drag, to get the absolute most efficiency out of the airplane.
So, we can go up and we can go forward. But what stops a plane from just rolling over or pitching up and down like a roller coaster? This is the final piece of our puzzle: stability and control.
To really get control, just imagine 3 invisible lines running right through the plane. A plane can roll from side to side around the line that goes from nose to tail. It can pitch its nose up or down around the line that goes from wingtip to wingtip, and it can yaw its nose left or right around a vertical line going from top to bottom. Every single movement is controlled by specific little flaps on the wings and the tail.
But what's really amazing is that a lot of stability is just baked right into the plane's design. Next time you're at an airport, look at the wings on a passenger jet. See how they aren't flat? They angle up just a little bit. That's called a dihedral. If a gust of wind pushes one wing down, that angle makes the lower wing create more lift, and it automatically pushes itself back up to level. It's a brilliant, simple, self-correcting system.
And you know, that really just says it all. From the exact curve of the wing that creates lift, to the slight upward angle of those wings that creates stability, every single part of an aircraft is designed on purpose to arrange and balance those 4 invisible forces, making this whole miracle of controlled flight possible. So, there you have it. The puzzle is solved. The next time you're on a plane, you won't just see a wing. You'll see an elegant airfoil in a constant dance with 4 invisible forces, masterfully manipulating the very air it flies through. But what happens when you push that air past its limits? When you go faster than sound itself? Well, that's when the physics gets really, really wild. And that is a story for another time.